What I'm going to talk about is actually something that can only be done in printing. And I think now it's quite amazing that when we say 3D printing, suddenly everybody knows what it is. So I hope I can show you some new things that you may have not heard about in 3D printing. We are Stratasys. We are a leading company in the 3D printing area, or what is also called additive manufacturing. And we truly believe this is just the beginning, and it's a wide and wild world that is still waiting for us. Basically, if you look at how we get 3D content and how we do 3D printing, the sources of data are very many. Actually, we can take any 3D file that was produced either by a CAD software by an engineer, or by CT or MRI that was just mentioned, or by 3D scanners. By the way, nowadays you can find a 3D scanner that can scan your face, and we can print your face right there, and it's becoming a new idea for presence for people. So this is another way where you can get 3D file, and there are many new softwares that you can find either free on the internet or buy, where you can manipulate 3D data. We take all this data and we bring it into a printer, and right there you press enter and you get an object that was printed on this printer. This can be a model, it can be a prototype. Actually, prototypes are now the biggest market for 3D printing or for additive manufacturing. But we are now getting also into the world of making real parts for real use in aerospace and in consumer goods as well. The idea here is that basically you get something significantly faster than in any other production way. Sometimes you can save weeks, especially for new designs, weeks of waiting for the first prototype and get it right after a few hours. Normally, you don't need assembly. So instead of taking all sorts of parts and putting them together, now you print a whole full object at once. You can do very complex structures. Some of them are actually not possible in any other way than in additive manufacturing or 3D printing. The whole idea, started a long time ago. The Egyptians already knew it. The way we build is layer by layer. So once you have a computer file or software, the system can slice it into layers, and then you build layer by layer. This way you can basically make any structure that you want. And this is how 3D printing or additive manufacturing are working. Just if you look at what happened in the last 2 years, because I think if this talk would have been given, let's say, 2 years ago, most of you have not heard about 3D printing. But now it has become a talk, every housewife, every kid, every, person in the supermarket can tell you that he knows what is 3D printing. The reason is that the media attention grew significantly in the last 2 years, while actually, I have to say, the technology itself did not improve that much. Sales did improve by 50%. I'm talking about the whole market in the last 2 years, but the media coverage or the attention of the public has exploded really in the last 2 years. By the way, the whole market for 3D printing or additive manufacturing is now about $2 billion a year, which is quite significant, but it took a long time to get there. Part of this media attention, the result is that now Stratasys, which is actually an Israeli company, that is the product of a merger between two companies, Objet, that was started in Israel, and Stratasys, that started in the United States. They both merged in 2012, and we are now the fourth largest Israeli company on NASDAQ in terms of market capitalization. Actually, it's about $6 billion now. And I have to say part of it is due to the media and to the attraction of this new field. We have two headquarters, one in the United States, one here in Rehovot. The customers for this technology are from all the fields in the world, really. Everybody wants to make fast prototyping of every new product that they make. So all this list is are customers of us, from automotive, aerospace, medical, a lot of universities, of course, dental, jewelry, and so on. There is no Nike shoes that comes out without it being printed many, many times before the designer likes it and it goes to production. The same for cars. They print many, many parts of cars and so on. Lately, we also merged with another company called MakerBot. MakerBot is a company that makes small printers that you can actually purchase for your home. If between Stratasys and Objet, we had something like 35,000 installed machines worldwide by the middle of 2013. MakerBot already has more or less the same number of machines installed in homes or in offices. Small machines that may cost something like $2,000, $3,000, and you can play at home and make your own little things. So now they are also part of Stratasys. So a few words, very, very fast, about the main technologies that are used for additive manufacturing. Actually, most of them are not really printing. The technologies are different. There is only one segment of the whole additive manufacturing world that is printing. The first technology that I want to talk about very, very briefly is FDM. FDM is the technology of Stratasys from the United States, was actually invented by Stratasys, and it's called fused deposition modeling. The idea here is it's sort of an extrusion head, very, very fine head, where you have a filament of a thermoplastic polymer, you melt it, and when it's liquid, you can deposit it in layers as you wish, and make any structure that you want. The benefit or the advantage of this is that you can use a commercial or nearly commercial thermoplastic materials, such as ABS, nylon, Ultem, and so on. And you get the mechanical properties very similar to the original material. Another technology that is very common is SLS. SLS is selective laser sintering. In this technology, you start with a powder. It could be a metal or a polymer, and you have a layer of powder on which you have a scanning laser that sinters only where you want the structure to be built. So this is done with a layer of powder, layer by layer of powder that is sintered. SLA is another technology, stereolithography, where you have a liquid bath and you sinter or you cure or you actually make a chemical reaction with a laser only where you want within this bath. And then there is Polyjet. Polyjet is the technology of Stratasys that started in Israel, and it's an inkjet technology. It's really 3D printing. It has multiple heads so that you can, and I will talk about the advantages of this. Why it's in orange? Because this is the technology I want to talk about, because this is actually the only technology between all these that can do multi-material and not just a single material. And this is a very big advantage, which I want to talk about. And is the subject of this talk, of course. So within Stratasys, FDM is actually is half of our business, more or less. It was invented in Stratasys, but Polyjet, this is the technology that I want to talk about, enables us to do multi-material printing. Just to give very, very briefly the history. So Stratasys in the US with the FDM technology started in '88. Objet started in 10 years later with the inkjet technology. And in 2007, we introduced the first time an inkjet printer that can do multi-material. And this is where the promise is that I want to talk about a little bit now. So let's look once more about how 3D printing can be done. If you take an object, you can think that you can divide it into little boxes like this, and these are called voxel. What is a voxel? Voxel is a volume pixel, okay? So the smallest unit that you have within an object is a voxel, and the size of the voxel depends on the technology that you use. Basically, you can think about it as a similar way to 2D printing, sorry, where you have pixels. Now you have voxels. And if you think about Lego, of course, has a sort of a voxel. The smallest one is this little Lego brick that many of you may have used. This is the voxel, and the others that are bigger are made of few voxels together. Now, how is this compared to what we do in 3D printing? So actually, our voxels are significantly smaller, and in this little Lego brick, we have 4 million Polyjet voxels that are the result of the size of the drops that we print with the inkjet. And you can imagine what kind of resolution is possible. So if you look at our machine, what you have are lines of heads, inkjet heads, and some of them can print one material and the others can print another material. And we also have to print a support because whenever we want to make something that has a hole in it, we need to have a support inside so that it doesn't collapse. And you can think about it as Lego bricks. So for example, you have one material to make a model, another material to make a model, a third material to make a model, and a support. And you can build something like this based on many, many voxels. Where you want to have something with a hole, you put support inside, which can be washed later. But this is mainly the concept of the 3D printing. Now, what can you do with multi-material? The first thing that you can do is very straightforward. These are objects that are made of more than one material, soft and hard, and so on. For example, if you look at this car dashboard, it has light material, dark material, rubbery material, hard material, and so on. And you can print the prototype of this dashboard with a multi-material printer so that you can have the lighter color, the darker color, the rubbery material, and so on. So just in one print, with no assembly, you can make this object that has more than one material in it. The more exciting, actually, side of multi-material, probably for scientists, is what we call digital materials. In digital materials, we can mix voxel by voxel with very good control. We can mix different materials. So something that may look like this, it's a bit difficult to see, I think, but every voxel can have a different material in it. And in this way, you can get new, very new performance or characteristics. So what do you do with the multi-material? You can make You can make a model of, for example, this foot with more than one material. You can make new designs that are very interesting and can open the world for new ideas. And you can get new performance, which I will talk about in a minute. For example, let's say you have a black rubbery material, and then you have a white rigid material. Now, if you print them in a mixture, depending on the ratio between them, you can get a gray scale, and you can get a scale of shore hardness. And this is something that we do. What you see here is a strip with the white rigid material on one side, with the black soft material on the other, and the whole range of color and hardness. For example, this shows the graph of how the hardness depends on the amount of rubbery material in the mixture. And you can see that you can get from shore A of 100 to, let's say, 35, just by changing the ratio in the printing. You don't need to develop a new material. You take two materials that exist and you mix them during printing controlling each voxel by itself. What happens if you make more complex ideas? I mean, for example, you can have a random distribution. You can have certain order, such as lines or domains. What happens then? What will be the properties of the material? So we've done some work, simulation work, with a group of Hod Lipson in Cornell. And this is what comes out. What you see here are objects that have different ratio and different order of soft material and hard material. And then when you have stress on them, they behave differently. You can see that each one bends differently, depends on how you distributed the hard voxels and the soft voxels. And if you actually go and do that, so for example, you have here layers, and the simulation shows that it will distort in this manner. And indeed, when you print such layers, and you can see that the distortion is indeed as was simulated by the simulation that we used. Where is this very useful for us? So actually, we print acrylic materials that are UV curable, and we have some limitations that are very difficult to overcome. And it's not just us, actually stereolithography has the same limitations. And this is between the toughness of the material and the heat resistance. So whenever we go to very tough materials, it means that they are basically softer and their heat resistance is bad. While when we go to a good heat resistant material, they become hard and brittle and they break and their toughness is not good enough. So what we did, using all the knowledge that we had at that time on digital materials, we chose this very soft and high toughness material. And then we chose this high temperature resistant material that is very brittle, and we mixed them in a very specific way as was simulated and as we understood it will work. And this is ABS material. ABS is a good plastic that is used for many engineered applications. You can see that it has good heat resistance and good toughness. And by mixing these two materials, we got here. So completely out of this curve where we used to be, into something that is much more similar to engineered materials. And of course, this is very important when you make prototypes and you don't want them to break. So I want to show you now a scientific experiment on the brittleness of our materials. So this is the first material, which is somewhere in the middle of the curve. You can see it broke very easily. Now this one is softer, higher toughness. It breaks. We go to a higher toughness material, which is, again, lower heat resistant. You can see that it doesn't break even at that height. But when we climb a ladder, it breaks. And now we do the reference, or it breaks again. Okay? So if you grade them, you can do 1 meter, 1.5, or 3 meters with our normal materials. And now we go to the digital material. This is one of our chemists, Avi. He has a black belt in karate, and still it doesn't break the material. Still doesn't break. You can see it's quite a complex structure, but nothing broke, not even a small piece. Still doesn't break. So now we do the real difficult test. This is our building. Chemistry is on 4th floor, and it still didn't break. Okay, so you can see that by having multiple materials and digital materials, we can go into completely new properties that were not available when we had just single material. Another thing that we do is the design. And this work was done with Neri Oxman at MIT. This is from an exhibition in Pompidou Center in Paris, where she did these very interesting designs. If you look closer at them, you can see that these designs are very, very complex in terms of structure. Probably it's almost impossible to make such a structure in any other way than in 3D printing. But also you can have a very, very interesting mixture of color in a very, very detailed way that is possible only with multi-material 3D printing. We were talking about MRI, so phantom for MRI are materials that have the densities that are similar to our bodies. And you can see that we are able to print. This is the printed hand, and it looks in the MRI or CT, by the way, in a similar way to a human organ by having the ability, to mix materials with different density that looks either like bone or like soft tissue. Another interesting thing is to make self-assembly. In this example, what we do is we print 2 materials, one that stays the same and the other that reacts in the environment where we are. So for example, this work was done also with a group in MIT. And here, what we have is material that is water absorbing and material that is not water absorbing. The simulation shows how they should behave. This is the printed example. And now I want to show you how it works beautifully. And actually now it has a new name, which is 4D printing already. It's not just 3D. So you have the printed object in the water. These areas absorb water, and these do not absorb. And you can see that it creates movement and self-assembly into a structure that was pre-designed and is in a controlled manner. You can get where you want to get. So what about the future? We believe that inkjet has its own kind of Moore law, not exactly as chips, but in a similar way, drop size becomes smaller and smaller, and printing speed becomes higher and higher. And you can imagine that in this way, our voxels can become smaller, and that the structures or the new materials, the new digital materials that we may be able to make become much more variable, and we can make many, many new things. We just need imagination to think about them. So for example, you can easily make now full color, full color by just mixing colors as in 2D printing. So if we have cyan, magenta, and yellow, and of course we will have to use also white, black, and transparent. So within these 6, you can probably get any color that you want in the world and start to print pictures or skin tone on anything like that that we may want. You can think about printing conductive lines within an object with no need for assembly and no need for having wires in there and so on. So this is another interesting challenge. And as Nir mentioned, we joined the Magnet program in order to be able to do that. You can think about bioactive materials that you may be able to print tissues. You can think about chemically active, all sorts of catalysts or other things. You can think, if your drops become small enough, you can think about nanoscale shapes and real new materials that are designed. Instead of compounding a material, you can actually build it bottom up in any way that you want by multi-material 3D printing. So we invite you to use your imagination and come to us with new ideas. As you can see, we collaborate with many universities and with many companies as well. And I want to thank, first of all, 2 people that contributed a lot to this talk, Dr. Ofer Shochet and Dr. Daniel Dikovsky, and the whole scientific group in Stratasys. Thank you.